Welcome back to AP Calculus with Mr. Walton. Today we're going to talk about volumes by integration. Section 7.3. So we're going to look at example number 1. A solid lies between planes perpendicular to the x-axis. Cross sections are perpendicular and they are semicircles. And we have a diameter that's going to be given based on our functions f of x and g of x. Let's make a picture first. All right. So if we make our beautiful picture, we're hoping that f of x here in pink looks something like this. And then we're hoping that g of x looks something like this. And we're talking about this being 4, down here being negative 4, this being 2, this being negative 2. And we want to find, using the highlighted area, we want to find volumes that contain semicircles. So if we're looking at those semicircles, we're going to say here is our diameter, and it would come up like this in 3 dimensions. It would be facing into us. So what we need to realize is, what is our radius here? So we're looking at a radius that's just going to cover this highlighted in purple and yellow. So if I look at that, I'm hoping that you guys will see that our radius is just going to be 4 minus x squared. All right. Hopefully that makes sense. Now, try to set up the integral. I'll show you mine in just a second. So hopefully you got that the semicircle area is 1/2 pi r squared. Therefore, we can set up pi over 2 times the integral from -2 to 2, because we're going to take these semicircles and we're going to move them from -2 to 2. And we're going to use our radius, 4 minus x squared, and we have to square that value. So then we're going to do that, and we're going to hopefully expand this, if you would, just to show you if you're doing this by hand. So that we get a nice trinomial. Then we're going to say, okay, we've got this. All right, so that we have pi over 2 times the quantity we would plug in or use our calculator, and the hope is that you get either 256 pi over 15, or as a decimal, 53.62. All right, moving on to example number 2. Okay, what if we have a region that is revolved about the x-axis to generate a solid, given the information here? Okay, you guys try to set up the graph. I'll have mine set up, and then we'll move on and we'll go from there. Ready? Try it out. Okay, so we have our picture, and we're talking about revolving it around the x-axis. Okay, if we revolve it around the x-axis, I'm hoping you guys see it's going to revolve like this, so that we're going to have an oblong shape. I know mine's not exactly, but we have a set of, in this case, discs that we can use to find this volume. We have all of these, so now I need to figure out what is my radius. So if we look from here to here, this would be a set of radii as we're moving through. So then r is equal to 15 minus 2x minus x squared. We're talking about the area of a circle, so we're talking about pi r squared. So then we're talking about integrating from -5 to 3, and we put our pi out front since it's a constant, and we have 15 minus 2x minus x squared squared dx. Then we can use that to solve by hand if we need to, or we can use our calculator, and if we do this correctly, we should get 16,384 pi over 15, or 3,431.46 rounded to the nearest hundredth. All right, so it gives you an opportunity to see the setup, of the integral. You can practice by hand, you can practice inputting this into your calculator, and here are the correct answers. Moving on. Example 3. Okay, we have a region in the first quadrant. It's revolved about the x-axis, and we want to find the volume. All right, try to set this up using a graph, and then we'll move on from there. All right, so here is a nice little picture so that we can see. I've done a little different colors. We have f of x in green, which is our 4 minus x squared. We have g of x in red, which is our 1 minus quantity, 1 minus x squared. And then we have our boundary of the y-axis. I've done that in orange, and then I've shaded the region in orange slashes so that we can see this. Now remember, we're going to revolve it about the x-axis. So when that occurs, I'm hoping that we can see that we're going to have one circle that's created by our g of x and another second circle that's going to be created by our f of x. When I put those together, it may not look like a nice washer, but it is a washer. Okay, if we're talking about washers that we need f of x and g of x, we need to establish which one is the big R, which one is our small r for our two radii. So capital R in this case is going to be our f of x. It's on the outside. It's the larger portion. And little r is going to be 2x minus x squared, which you can see is our simplified g of x up here. And then we're going to set up our integral. Since we're moving along the x-axis, we're going to move from 0 to 2. I'm going to have pi up here, and I'm going to have r squared minus r squared. And we're going to write this in terms of x's. So then I'm going to fill that in as pi from 0 to 2 of my quantity, 4 minus x squared squared, minus my quantity, 2x minus x squared squared, all in terms of x dx. Now then, from this point, you can expand, combine, do this by hand. You can plug it into your calculator, and therefore, if we've done everything correctly, we hopefully get 16 pi for our answer, or we're going to get, in decimal form, 50.27. All right, now moving on. Example 4. Find the volume analytically of the first quadrant enclosed area formed by the axes and y is equal to 16 minus x to the fourth, where the cross sections are squares. All right, try to set this up graphically, and then we'll look and analyze this problem. All right, so if we look at this, hopefully you've got a beautiful graph. We have our two intercepts at 0, 16 and 2, 0 for this. We're also going to realize that we have the enclosed area, which is bounded by our axes. So you see me filling it in now with the highlighting in yellow. And we're going to use cross sections of squares. So I've tried to have these sort of at a slant so you can see that they're coming out of the board towards you, and they're squares. If they're squares, therefore we're looking for a side length. In this case, our side length is our nice function, 16 minus x squared, which then means we're looking at the area for this to be s squared, and we want to find the volume of this enclosed area in terms of squares. So we're going to integrate from 0 to 2. We're going to take 16 minus x to the fourth squared dx. And from this point, you have a choice. You can expand, you can solve, or you can use your calculator. We have lots of different choices. My hope is that you get 364.09 rounded to the nearest hundredth. Okay? As a reminder, okay, we have three methods that we have talked about in section 7.3. Number one, we have discs. Number 2, we have washers. And number 3, we have shells. Now remember, those are cylindrical shells, and they are the rectangles formed on the outside of that. And what I want to point out is that we first analyze, is it okay to use disc? If not, we would check, is it okay to use washers? If I can use washers, a lot of times I can still use shells. But what I need to remember is, if washers and shells are both possible, their orientation is opposite. Okay, so what I mean by that is, if washers are dy, then shells are going to be in terms of x. If our washers are dx, then our shells will be in terms of dy. So keep that in mind when you're looking at which method best works for you. All right? Hopefully this helps. Good luck, and we're out.